Namaskaram everyone. Welcome back to the 24th episode of our Master Unreal series, and this is also going to be the last episode of distance matching where we are going to implement the stop state. So if you haven't watched the previous episode, I highly recommend you do that because in the previous episode we did the distance matching for the start state, and over there I explained how the evaluators, distance curve, how the blending and duration and everything works out. And then you start with this video that will help you to synchronize with all the stuff that we have done so far. If you are not following the Locomotion series, I recommend that you do that so that you can understand where certain variables are coming from. And if you have any questions, you can always pin down in the comments. So without wasting any time, let's get started. Okay, so we are in our editor now. Okay, before this, I wanted to make a correction. First, that is from stop to start, we unshare this rule, we make it independent. And in this, we only want to check if the key was pressed. So then only we will transit, because there is a situation when you can have velocity even when you are not pressing the key. So let me show you. If I play and change this to ABP base, just observe this acceleration, which is the input key, and the velocity. You can see how quickly the acceleration took up to 800, but the velocity took some time. Now if I release my W key, see, there was a delay in the character velocity because character velocity was gradually decreasing and the acceleration immediately became zero. So in that fraction of times, the frames, we will have the velocity, but we will not be pressing the key. So the stop to start transition should only happen when you press W or some other movement key while the stop transition is in the process. Okay, so that's the reason I made it independent logic instead of sharing it. So we can also unshare this one since we are not using it anymore. Now we can hit compile, and like we did in the start, we will go here and search for all the stop animations, and then right click, asset actions, edit selection in property metrics, and we want to apply the root motion and the compression, and the compression would be the one we created last time. So go in the animations, select this one and apply it here, save. All right. Also, again, select all the stop animations, right click, animation modifiers, add modifier and apply the sync marker. Press yes, apply to all and yes. Okay. Now, if you check, the distance curve will be available in all and the foot sync markers is also available. Save all. Go to ABP base, and now we are going to implement the stop layer. So go to Locomotion layers base, and in this open the stop layer. Again, we are going to use the sequence evaluator like we did in the last episode for start, and we are going to create the become relevant function and we will bind it. Let's name it setup stop anim. Since we have understood everything, how the evaluator and the binding functions and distance matching works, we can implement it real fast, and we can also do for the update. So update stop anim. Okay, the sequence will be dynamic, explicit time would be dynamic, and it should not loop. So that's the overall settings we did last time as well. Compile, go to setup stop animation. Now we need to select the sequence. So I'll create three variables, that is jog stop cardinals, and I'll name it anim struct cardinal directions. We'll create two more, and let's name it crutch stop cardinals. Then we name it walk stop cardinals. Okay, these are the three. You can put them in a category. So anim set stop. Okay, so we have three animations. Let's bring them here. Now we will convert this to sequence evaluator. So use the pure function. Then we are going to set the sequence, this time without inertial blinding. So let's first set the sequence. I'll go for select. I'll request a property access node. I will check if the character is crutching. If that is the case, then we would like to go for the crutch cardinals. I'll go forward. Now, if that is not the case, then I would like to go for select again. And I'll duplicate this. I'll check if character is running. If that is the case, then we will plug in the jog, otherwise walk. Okay. So we will create a function that is going to tell us if the character is slowing down, or basically whether should we apply the distance matching or not. So should distance match stop. And when is that going to happen? The same rule that we added earlier is get the property access, duplicate this, get whether you are first get the has velocity, and another one would be is accelerating. So if the character has velocity and the key is released, so use the negation, because if the key is released, no acceleration. We'll plug it here and mark it pure, thread safe. Okay. And now you can go back to setup stop anim. So we will call this function and we will check. So if the input key is released and there is a velocity, that means the character is naturally slowing down. In that case, we don't need to apply any kind of distance matching. But if that's not the case, then we should apply the distance matching. And for this, I will call distance match to target. So the distance to target here is how far the character still needs to move before stopping. And we will give the distance to target 0, and the sequence evaluator will be coming from here. And the location curve would be this. Cool. Since that condition is no longer true, that means the character is almost stopped or it is barely moving, because there is no input key. There are only two situations that can happen. Whether you have pressed the key and it is hardly moving, or it doesn't have the velocity. That means it's barely moving or it's basically almost stopped. So in that case, we just straight away want to jump to the 0. So that's the reason we are putting in the false. And now we can go to update stop animation. Now here again we will check whether you have velocity or not. Then only we want to apply the distance matching. Remember, if you do not have the velocity, then distance matching won't work. So we need to ensure that the character has the velocity, otherwise we will just normally play out the animation. Because ultimately our goal is to adjust the play rate. But if your character does not have velocity and you do not have any speed or play rate, that means we can just play the normal animation. I want to use the advanced time node. I'll pass the context. We will get the node, convert to sequence evaluator, pure function, connect this. So now since you do not have any play rate, we will just use the same play rate of the animation and we will play out the stop animation as it is. But if you have velocity, then we have to pick frames accordingly. So for this, we will go in the true situation. And now we need to calculate the stop distance. So we are going to create a function, get predicted stop distance. And now we need to predict the ground movement stop location. So this is how Unreal calculates. So first I'm going to get the velocity, and to get the velocity we have to create a function that will get us the movement component. And here I'll add the property access. I'll go for try get pawn honor, and here I will get the movement component, and I can cast to character movement component. I can connect this one to this one, and you can return it. Plug this here. If this fails, then return nothing. Mind the sensitivity of letters casing. So return value R and V should be capital, no space between these two words. Save and compile. Now this will get you the character movement component, and now you can access all those parameters that we were setting. So make this function thread safe and pure. Go back. You will find the movement component and you get the last update velocity. Then we will again create property access node. Let's duplicate this a few times, and we will use the movement component, use braking friction. So B use separate braking friction, connect this one. And now we want the braking friction. So braking friction, connect this, go for braking friction factor and the braking deceleration. Walking. Okay. All right. We have everything. Now get the vector length to get the magnitude. Actually, we should get the vector length in XY because we don't have any motion in DZ. Okay. Now save and compile. You can mark this function thread safe and pure. And now you can tell the Unreal when to stop. What is the stop distance? So I'll get this get predict stop distance, and I'll promote this to a local variable, and I call distance to match. So this is what we will call, and we can plug this in true. So now if this distance to match is greater than 0, then only we would like to go for the distance matching. Otherwise, we will just normally play out the animation. So if it is greater than 0, then we will do the distance matching. Otherwise, we will not. So there are 2 pins coming in, and we will use the distance match to target. And let's connect this return here. Now you can get the distance to match. The sequence evaluator, just copy and paste it here. The location curve name. Okay, so that's it. So now you have the distance matching based on the velocity. And now you can go back to your locomotion stop and you can remove this. Cool. Save and compile. And now you can go to unarmed layers. Okay, so just to save time, I have already placed these animations. You can pause the video and place them to their respective places. So after setting this, just save all. And once you are done, you can play. You can see it is stopping. If I press shift and I hold W and then I release the W, it stops. So if I crutch and I stop, it takes this transition. If I slow down the time and I release the W key, you see it stopped properly. Cool. I want to add one more rule in the start and cycle. That is, if you change the state, if you change your crutch state, that means if you are crutch and you stand up or opposite, then we would like to transition to idle or cycle. We do not want to play that stop animation. And I'll give the automatic rule second priority and the crutch state change first priority. So I'll get the crutch state change. I'll connect this. Do the same for cycle. The automatic rule can be first and this one has to be second priority, and go for the crutch state change. So if this changes, then we are going to transition as well. All right, now save all. So you remember this locomotion direction variable that we created in the start of the series? We are going to use that to pick the animations from different directions. So I'll go to locomotion layers base, and in the setup stop animation, I'll use the property axis node. I'll get the locomotion direction from there and I'll go for select. Now you can duplicate this or just delete this one. You can plug the forward, backward. Okay, this goes here. Now you can duplicate this, go for select again, plug it here. Okay, and we pass it here. Do the same for crutching. Just duplicate this entire thing, disconnect it, delete this one, connect all the pins. Alright, so we have everything now. We can just copy this entire thing, except this one. Copy this and go to setup start animation, and we can do the same thing here. So I'll just paste it. But this time we are going to get rid of this walk crutch and we are going to bring these two here. Delete this, put it here and place them here. Okay, and this would be the sequence. Now real quick, just plug the animations of start, just like we did for the stop. Man, Unreal is buggy. Why this debug data popover is glitching? Okay, now save all, compile, and now you can play. You can see the right, it starts and stops. If you go front, start and stop. If I run, it starts and stops. But if I go to left, do you see this snappy leg behavior? That is happening because of the stride warping. We are applying our stride warping too early. So if I escape, if I go to locomotion start, do you see this stride warping? The minimum threshold is set to 0. That means the stride warping will immediately, it will kick in with the full force because we have set the alpha to 1. Now if I set it to 10, the stride warping will start when you have at least threshold of 10 meter per second. If you try now, see, it's hardly showing any behavior. I'm releasing my key real quick, and now if I gain some speed, you will still observe that snappy behavior because the stride warping is coming with a full intensity. If I go in right, it works fine. But in case of backwards and left, it still goes little snappy because you are coming with a full intensity, and we need to control this intensity based on the animation's timing. So what I mean by that is if you go to Lyra animations and search for left stop, now I want you to observe this in the left stop almost at 0.15 to 0.17 your leg is on the ground, and that's where the stride warping should kick in. If I try some other animation, let's say forward stop, if I go again, you see at 15 my leg is about to be placed, and by 0.20 it is placed. So it's like from 0.15 to 0.20 should be the starting point when the stride warping should kick in, and that too in a smoother way, not with a full intensity, full force. If we give alpha 1, then it will apply the full warping. We do not want to apply full warping. We want to apply it naturally, smoothly, and gradually as we progress. The same thing we did for cycle. We were calculating the stride warping cycle alpha. We are going to calculate the stride warping for start as well. So I'll create this variable. See, you only need stride warping when you are in a motion, when you have a speed. But when it comes to stop, you are slowing down. So there's not a problem. But when you are starting up, that's a problem. So I'll go to Locomotion start again. And first thing, I'll set the threshold to 10. And then I'm going to plug this start alpha. Also, let's apply orientation warping to adjust our spine bones as per our facing direction. So I'll call orientation warping. And the orientation angle would be property axis locomotion angle, the one we calculated earlier. And we can add the bones real quick. Add all the spine bones. Okay, so I've added all the bones. And also let's change it to graph. Connect it again, and the minimum threshold should be at least 80 meter per second. Now let's calculate the stride warping alpha. I'll go to setup start and I will set the stride warping start alpha to 0. That means no intensity. The stride warping is not applied when the animation is started. Okay, we will wait up to 0.15 seconds and then we will start hitting in with the stride warping slowly. Okay, so for this I'll go in the update start anim, and here first I want the time, how much time has been passed. So I'll create a local variable, call it explicit time. And remember in the last episode we talked about how the time gets accumulated. That's what we are going to use to get how much time has been passed. So in the sequence evaluator, I'll just pull this a bit back, and here we will get the accumulated time. So this will tell us how much time has been passed. Once we have the time, we can apply this stride warping. So I'll get this, connect it, connect this one. Let's break this and get the context here. Cool. Now, if you increase your speed up to, let's say 200, 400, then the stride warping alpha might cross 1. It may become 1.5 and 1.6 or 2, for example. We don't want that. We want to keep it in a range of 0 to 1. So I'll use map range clamped. And here we need to calculate the alpha. So first, how much time has been passed? Subtract the offset. That means you will start from 0.15. So we will create a variable stride warping blend in start offset. Now this is a approx value that we have seen in multiple animations. So we will consider the common value. So let's say 0.15. As soon as this time passes, we will start blending in. So this would be the value. And now we need to tell the blend in duration. So just like we have in transitions, we will provide here as well. So stride warping blend in duration scaled, and we want to do it for 0.2. Let's say for now, just like we have in the transition rules, we will start with this and then we will adjust this based on the experiment results we will do right now, and the out range would be 0 to 1. Okay, now this is our stride warping alpha. We also need to adjust the play rate so that it matches with the stride warping alpha. I'll make a vector 2D. We need to create another variable. So we'll say play rate clamp starts pivots, and we will call it vector 2D. And the play rate we are assuming is 0.6 and 5. We'll bring this here, we'll split it, and now we will use the linear interpolation that would go in X, Y would be as it is. And now we need to provide our alpha. So let's get our alpha because it is calculated here and it should go in B. And the blend in duration is 0.2. So we will provide our alpha and it will be linearly interpolated between this blend in duration, that is 0.2 to 0.6. And that would be our X. Y will go as it is. Now if I hit compile and now if I play, you see the snappy behavior is reduced up to some level, but still it's there. Up to some extent, it is still there. We need to control that. So we will increase the blend in duration, let's say by 0.5, so that it becomes more smoother, and it will increase the blend in time of this tide warping. And now if I try, it is much better, right? If you try back even, it's absolutely working fine. If I start running, if I play and if I'm stop and I do crutch, it was little fast. So I'll change this crutch state change to initialization. Okay. And now if I compile and play again, you see it was much better, right? All right. So I think we still have some time. Do you remember this from the third episode where we define how the locomotion angle is calculated, and based on that, we calculate the direction, which was the ideal case that will only satisfy if you are a keyboard player. So if you have a PC and you're using keyboard, it would be working fine. But when it comes to the controller, you will not have that level of precision where if you go minus 45 and if you just tickle slide in left or right, the direction will change. So we don't want that to happen. So to handle the controller's case, what I'm trying to say here is if you are continuously moving, then we will increase this minus 45 to 45 degree to, let's say, 55 or 60 degrees, so that you have more area for the forward, so that even if you tickle your hand left or right a little off than the 45 degree, let's say by up to 50 degree or 55 degree, then it should be fine. You will not go left because you cannot keep your finger up to 45 degrees all the time. So we just increase the coverage area if you are constantly running in a direction. But let's say you stop for a fraction of millisecond and you change your direction to left and right, then in that moment we will keep this ideal situation. So what I mean by that is when you move your analog stick back to the neutral position, or and you decide to switch the direction, then we will go for this ideal case. But otherwise, if you are going forward or backward, we will just increase this area so that you do not go left or right because of less precision. So this is something that I picked up from Lyra, where I saw that they are dealing with the controller issue separately by introducing this dead zone concept. So we have to help the user by increasing the dead zone so that direction switching doesn't become a problem. So let's get started in this. So we have this calculate locomotion direction. That is what we did last time, purely going for the ideal case. Now we will consider this dead zone which can happen in the game controllers. I'm just going to remove this update locomotion data from the blueprint thread safe. Okay. And we will go to velocity. And here we will calculate the locomotion angle first. That is the normal situation. So locomotion angle. And the way we get it is by calculate direction. The velocity would be character velocity 2D, and the rotation would be the character rotation. This will give us the locomotion angle. We also need to calculate the locomotion angle with offset. So locomotion angle with offset, and go for this, put it here, and we will get the angle and we will subtract root your offset. And the next episode we are going to implement turn in place. So over there I will explain the significance and why do we need this root your offset. Okay, so for now just go with this. Then we want to calculate the direction, so go for the locomotion direction, and here we need to create a function that will consider this dead zone issue and will give us the result. So I'll name it select locomotion direction from angle, and there will be 4 inputs. First is the angle that you have calculated from the formula. Then we have the dead zone. So how much you want to exceed more than the ideal case. So that would be, let's say 10 or 5, whatever you think is suitable. You can experiment as well. Take a controller, see up to what angle you like you should move forward or forward left, and based on that you can keep this dead zone. And then we have the current locomotion direction that we have calculated. So locomotion direction that was there earlier, and should we use the current direction or not, the one that is there. Now the locomotion angle can be negative, right? So we will first get the absolute angle. So we just care about the value, not the direction here. So we will get the absolute of it. You can check out the episode 2 and 3 to understand how this locomotion angle is calculated, why is it needed, and what's its significance. Now we have two dead zone. One is forward dead zone, another one is backward dead zone. These are the local variables, and that dead zone would be the one we will have here. So dead zone, and this is what we want to keep. We can connect this one directly since we are sharing the same value. I'll go for a sequence node. So get the use current direction. So if you want to use the current direction, then we will switch on E locomotion directions and we will get the current direction. So we'll set the forward and backward. If you are moving forward, then we will increase the dead zone so that even if you move your analog stick a little left or right, it will still move forward, and it will not go in the left direction. And if you are moving in left or right, we will keep the dead zone smaller so that you don't rapidly switch between the directions. But if you are moving forward, then let's double the dead zone so that you can keep moving forward. And same goes for backward as well. So we'll just multiply by 2. Do the same for backward. Change this variable to backward dead zone. Okay, once this dead zone is handled, we can go for a branch node, and now we will take the absolute angle. If it is less than or equal to 45 degree plus the forward dead zone that you have calculated. So if it is less than or equal to, then we will just return forward. So let's create one direction, and that would be forward. And if that is not the case, then we will go for branch node again, and let's just copy this and paste it here. And if the absolute angle is greater than or equal to 135 plus the backward dead zone, so let's change this, then you are moving in the backward direction. Again, I would highly recommend you check out the second and third episode to understand how these values are calculated in the ideal situation, and then you will get this one as well very easily. And now it's only about right or left, so we can just get the absolute angle. If it is greater than 0, that means it is right, otherwise it would be left. Okay, that's it. That's all you need. So save and compile. You can make this function pure and thread safe. Go back to update velocity, and now you can get that function here. You can connect this. The angle would be locomotion angle with offset. And just a correction, this dead zone is this. We should rename it to locomotion dead zone. We should remove this and get the dead zone from the input actually. This should be subtract node, so I'll get subtract. Let's remove it. The backward zone will be here, and this would be 135. So this has to be subtracted from 135. Right, now compile, go back, and here you can provide this dead zone. And the direction would be the locomotion direction that you have initially. And do we want to use the current direction? That will be determined if you were moving or not in the last update. So was moving last updates. So if that is the case, so if your movement changed, then we would like to use the correct direction based on that value. So to update this, we will go a little back, and here we will break this and we will update it. So if the local velocity vector is 0, and do the negation, not boolean. So if it is not 0, that means you were moving. So now we can go back here, and this is the locomotion direction with the offset, and now we want the locomotion direction without offset. So I'll just create a variable locomotion direction with no offset, and I'll change the type to E locomotion directions. We can bring this here, and now we will provide it the locomotion direction angle. So give it directly. The dead zone would be the same, so locomotion dead zone, and we need to pass the locomotion direction with no offset, and this is what was in the last, and should we use it again if you were moving? Okay, so in the start and stop we will use the same locomotion direction, but in the cycle we're going to go inside update cycle anim, and we are going to change it to locomotion direction with no offset. And in the locomotion start, this locomotion angle should be with offset. So I'll get in the main thread and locomotion angle with offset, and you can tweak the distributed bone orientation alpha by 3/4, so that is 0.75, and also remove the locomotion direction and the alpha from the locomotion cycle. We don't need them anymore, and you can keep this locomotion angle for the orientation warping, and you can change the threshold to 80 here as well, and you can also change the distributed bone orientation alpha to 0.75. Okay, so before I wrap up this video, let's implement this root yaw offset. So for now, we will just implement a simple root offset formula, that is to get the control rotation from the pawn owner. And let's duplicate this and change this one to get actor rotation. Once you have this, you can split these two nodes. You need yaw, so that is this. So subtract the controller's rotation and the actor rotation. Once you have this, normalize this between -180 to 180 and plug this here. This is your root, your offset. We'll remove this and we will implement it properly as per the turn in place mechanism. And if you have been following the series, you should know that the jump sources will also include the start and stop. So let's include this. Now if I do an jump, this should be fine. And now if I play, I can start in the forward. I can do forward left. I can do backward left. I can do backward right. I can even run in the forward. I can run in the left. I can run in the right. So that's it for this video. Like it, share it with your friends, subscribe to the channel, join the Discord community. If you have any questions, doubts, share it on Discord. Feel free to post the screenshot or your code. I'll try my best to help you out, and I'll see you in the next video where we are going to implement the turn in place. So till then, stay tuned.